Okay, so we're talking transformations of a function. This follows on from function notation, because what we're looking for is to understand and apply how what I write in function notation can tell me what happens to the graph of the function in terms of transformations. So we had here that translation, reflection, stretch, rotation are the transformations we know about. The translation of a function was what we were working on first. So this here is the vector of translation. So x and y. So if it moves left and right, up and down. So then we looked at if I have f of x plus or minus a particular value, it applies a translation of 0k in whatever direction. So if it's plus k, the whole graph will move. Plus k, the graph will move to the right. No. Up.
Up. Sorry.
Okay, it moves up. If it's minus k, it will move down. And I said that because all of a function, the graph of a function, is the relationship between the x and the y coordinates. So we've done it where you put x into a function and that gives you y. If you then add a value onto the y, the function doesn't actually have any impact on that final value. The adding k doesn't impact the function and the relationship. So one thing to add here, what I would say here is we are working outside the function. So when you're working outside the function, you are just adding a value to the end of the whole process. So it doesn't affect the function itself. So the graph, the shape of the graph is the shape of the function. So if you just add a value on, you don't change the shape of the function, you move it. Right? So we're working outside of the function. Right? So that's what I was saying here. Now, the next thing we looked at, well, you can add or subtract k, what's called inside the function. Now, the reason, anyone understand why that would be inside the function and the other one would be outside the function? What do you think? Any ideas?
Because this is what you had to us before you input.
Yeah, exactly. So I have to add a value to the x value, and then that whole thing gets put into the function. So the function will therefore change with depending on x, and therefore it will change the effect of k as well. Okay, so the function also affects the value that you add on. Right? So that's why we're doing it inside the function. And you can see how that's inside the brackets, it makes sense. Now what we were looking at was, well, the last thing we looked at was saying, well, if I do x add k, I think you noticed from your calculators that shifted the graph to the left. And if I do x minus k, it shifts it up, which seems to be opposites. So we were going to look at why does that happen. Okay, we're going to look at why does that happen. Did anyone have a read through and think, yeah, I know why it happens? Did you do any self-study by any chance? I know you do, because you love maths.
What's the fourth?
No, you've not done it. No? I know you can, though.
You're so mean.
I am a little bit. So that's what we're going to look at. So for all of you, a little bit of reading between lessons will help you. So we've got to look at why is it plusing moves it to in a negative direction, and why does subtracting move it into a positive direction. Okay, so the way we're going to look at that is we're going to look at actually what happens when I build these numbers up. So, for instance, I compared to if f of x equals x squared. Let's draw a table of values for this. Right, basics. Okay. So I'm going to pick my domain as to say -2, -1, 0, 1, 2, 3, 4, 5. Right. So if that's x, f of x or y will be what? 4.
So 1, 1, 1, 1, 1, 1.
Yeah. Not 2. 1, 0, 1, 4,
9, 16, 25.
Okay. Right. What I'm then going to do is I'm going to do another one, which is f of x plus k, which will make x plus k squared. So I'm going to look at that one. I'm going to do a particular one though. I'm going to look at f of x plus 2. Right? So what we're actually looking at then is x plus 2 all squared. Right? Now, we've got to try and think this through. I'm doing the numbers, I've not done the graph itself, we'll look afterwards. But what do we know is going to happen? What will x plus 2 all squared do to the graph of x squared? What will it do? What transformation will it do? Shift it which way? Left, so in the negative direction. How far? 2. Okay, makes sense, it's going to go left. So we know why it's 2 because we've got a 2. But what I want you to get into your head is I want you to think, why does it go left instead of if I add 2 on and shift it right? Because if I add 2 to the y, it makes it go up. That makes sense. But if I add 2 to the x, surely it would add 2 and push it up the x-axis. But it doesn't. It goes left. So let's try and think why. So I'm going to draw another set of a table here. Right? And what I'm going to try and do is make it clear why. Right? But you are going to have to pay attention. Right? Okay, so what I'm looking at is I'm going to use my x squared table, all right, in the same way that I'm going to I translate the graph of x squared. So I'm going to use these values to help me figure out those ones, rather than work them out directly. So I could work it out by doing, well, it's -2 plus 2 is 0, 0 squared is, I could do it that way, no problem. But what I'm going to do is I'm going to use these values, all right, and then think, well, can you then realise why the graph moves left? So this is the best way I've found of explaining it. So what goes in this box here for -2? Well, we know that, but I'm going to go for here. So what I do is to figure out what goes in x plus 2 squared, what I do is I look at the -2 for x squared, but then I have to go 2 spaces up. So that's what the x plus 2 means. So I start at this point, because that's where I am here, but I have to look 2 spaces up to this one. All right? What I then do is use that value, but put it in that hole. Okay? Do you understand? So that will be 0. So what have I done with the coordinate that I'm using? So what I've done is the x plus 2 bit is where I want to look to get my coordinate. But what do I actually do with the coordinate? I take it and I bring it back to where I want it. Okay? So for instance, if I now look at the 1, if I want to know what the coordinate is for 1, so I go up to 1 here, I look in the +2 direction to 3, I take the coordinate, but what do? I bring it back 2 spaces, so 1 is no longer 1, it is now 9. Okay, so this is the thing. The +2 doesn't mean what you do, it's where you look for your solution. So I have to look up the graph and bring it back to where I want it. Right? So again, if I look at 3, if I want to know the value for 3, I go up to 3, I have to look up at 5, okay? Take the value, bring it back. So it is 25. Now, of course, these values are easy enough in themselves to work out, but it's that whole trying to explain why the graph goes in the wrong direction. Right? So, is that kind of making some sense? So if I do it with the graph, all right, bear with me. Let me just... So, if I want to plot the points of, so this is x squared, if I want to do x plus 2 squared, same idea. So if I want to know what coordinates, so it's x goes y, so what y value goes with -4, what do I have to do? I have to think of -4, look to where? So I have to go up to -2. So I've added, that's where the add 2 comes on. I look at the coordinates that gives me, and then what do? I bring that back to where I want it. Alright? If I'm at -2, I want to know where the coordinate is. What do? I look in the +2. Look at that value, think what it is, and then bring it back with me, so it ends up here. So can you see why the graph actually shifts left, even though it's +2? Make more sense?
It's kind of like backtracking, right? In a way. Like with the
In a way, yeah. So what we think, you know, the +2 here, it's because it's applying before the function. It's not a direct result of the function. It's more like, well, I've got to. The +2 is not the direction of the transformation. It's the direction where you look to get what you need. Right? So that's why the +2 gives it a shift in the negative direction, and that's why if it's a -2, you look backwards, grab it, and bring it forwards. So that's the deal. All right. Make sense? Okay. Well, so that is a translation in the x direction and the y direction covered. Right. The next thing I want you to have a look at, and you're going to try and explain it to me, right, is the reflection ones. Alright, so it's page 23, top of page 23, the reflection. I would like you to be able to explain to me why that notation with f of x would give a reflection. So thinking of coordinates. So tell me why one gives a reflection in the x-axis, one gives a reflection in the y-axis. And think, like we've been talking, what happens to the coordinates? Okay? So give it 5 minutes, have a read through, try and figure it out. Okay, so I've got a graph up here. What it is not the issue. If we've got f of x, that's the function. If I asked you to explain what having minus f of x would do, what would you tell me and why? Gita.
It would reflect in the x-axis.
Why?
Because the negative side is outside of the function.
Yeah.
So it relates to the y-axis.
Yeah.
And so, since pretty much all the way.
That's what it is. Anyone want to finish that off? It's true, the negative applies to the y value, so basically you're not changing the x coordinate, but every y coordinate becomes negative whatever it was. So the ones that don't change are the ones that are on the axis, because 0 and negative 0 are the same thing. But for instance, this point here, if in the initial function it is 3, alright, after making it negative, the y value will change, the x value won't, so it will just go to negative 3. Right? This point is here, the x value doesn't change because the negative gets applied after the function, so that x will give that value of y, but then I just make it negative, so it ends up down here. Right? This point as well will go up. So we will end up with the shape being reflected, right, in that axis. Okay, it's not bad for freehand. So we get a reflection in the x-axis. Now, what about how would we explain if that's f of x? What does f of minus x do? How would you explain that? Yeah.
This is done inside the function, so it affects the x coordinates.
Okay.
So hence it reflects in the y-axis. All of the x. The
But
y
there's it's a bit more like the other one when you're explaining inside the function. A bit more needs to go into explanation. So go on.
the
Carry on.
y coordinates don't get changed, but the x do, because they're done before the input's put into the.
But surely if I make x negative for what it was, that will change the y value, no? Because you've changed the input, therefore the output will change. The y does it just become a...
It's what coordinates.
Pardon? But what you're trying to say is the coordinates have already been worked out, so it's just changing the y value. Which is what happens, but can we maybe think of another way of doing it, to explain it?
Just remember it how it is.
Well, basically it's this. Think of our table of values again. So I've got -2, -1, 0, 1, 2, 3. Basically what we're doing is when we pick an x value, and I want to know the y value that goes with it, what we do is, if I've got to work out the value that goes with -2, I actually look at the -2 to find the value. So what's -2? +2. So instead of working that answer out, I go to 2 and I take whatever the answer is there and put it there. And in the same way, if I want to know this one, I've got to look at -2 and whatever that answer is, I put it there. So basically, they swap places. Right? So that's what we do. So it's about, I have an x value, but the y coordinate that goes with it needs to be taken from the negative value of that x coordinate. Right? So they do a swap. And if we swap y coordinates, we are getting a reflection in the y-axis. Okay? So basically then, if I want to know the value that goes with -1, I look at 1, find this value, but put it over here. Okay? If I want to know the value that goes with -2, I have to go across to 2, look at it, well it's off, so it's going to be right down there somewhere, up here. If I want to know the value that goes at 0, I have to look at 0, so that one stays where it is. Right? So we end up with this point here, so -1.5, or 1.5, I have to look at -1.5, okay, and put that over there. So we do end up with, right, themselves. So I have a reflection in the y-axis. So we swap them over. Make sense? Okay. Next thing to explain are the stretches then. Have it in the same way, please. Okay, right, let's have a look then. So, first of all, I do it the other way around to in the book. Let's have a look at what happens if we do p times f of x. So again, if this is f of x, if I do something times f of x, again, inside or outside the function?
Outside.
So we're applying this transformation to which coordinate, the x or the y?
Y.
The y. So basically, let's have a look. If I did 2 times f of x, okay, that means basically all I'm doing is I put an x value in, I work out the y value, but then what do I do? Multiply it by 2. Now the thing about multiplication is, the bigger the number I want to double, the bigger the impact it will have, no?
Yes.
So that means the higher the y coordinate is to start with, the more impact that times in by 2 will have. Now, are there any values that will not be impacted by multiplying by 2? 0. So we know that any y value of 0 will stay where it is. Okay? Which points will have the most impact on them?
The furthest.
So the furthest one. So the one I'm going to pick to start with is this point here. So again, remember what I said. We take this x value here, whatever it is. We find the y value, whatever it is. We double it. So if I double that, it's going to be up here somewhere, no?
Yep.
So this here will be 2 times whatever y is. So that point will go up there. Right? And the same with all these other points. So this point will end up here. This point will end up way off the graph. This point here will end up here. This point here will end up down here. So what happens is, right, the graph looks like, well it has, what has actually happened if you had to explain? It gets stretched. Now what people make the mistake of saying is that it gets squashed, because it looks narrower, but it's not, it's stretched up. Right? It doesn't actually get squished in. It looks like this line has come in and this line has come in, but it's not actually what's happening. Alright? Which is every y coordinate gets doubled. So we can say that if every y coordinate gets doubled, we have a stretch factor, okay? A stretch factor of 2 in this case, every y coordinate gets doubled. So again, the one outside the function is quite simple. This point here, if the red line was down a bit, it would also be stretched down as well. Obviously, if I have a negative value, it gets stretched. Any questions on that? It's quite easy, isn't it, the stretch and whatever in the y coordinates. However, let's have a look at, again, if this is g of x, just for a second. What if I have g 2x?
You do a similar thing with how you did with the table, only instead of adding and subtracting, like you did before, you actually multiply.
Yeah, it's exactly what I was going to say actually, and also because it's not adding, it's multiplying. If I don't always look in one direction for the coordinate, do I? Right. So for instance, if I want to know, so this is -1. If I want to know what value to use with -1, I don't have to add 2 on and look that way. What do? I multiply that by 2 to figure out where I need to look. So that means if I'm in the negative zone, I have to look in the negative direction. So I would take from -2 and then bring it back. So that point would end up going here. Alright? Again, 0, what happens? It stays where it is. So that's different to the plus and minus. If I want to know where this point comes from, so it is here at the moment, but what do I need to do? Multiply by 2, so I have to go and look up. Now that's off my range. So this point will actually not be there, it'll be up here. Now here's the thing. The further away I get from 0, the further up I have to look for my new solution. Because obviously if I double 1, I have to only go to 2. However, if I'm at 3, where do I need to look for the value for 3? 6, so I go even further. So that makes it look like the graph gets squashed. Okay? Do any of the y values change? No, because we just kind of bring them in from both directions. So that means that the graph gets properly squashed in. So here's the thing though. So we still have a stretch, but in this case direction x. But what is the stretch factor of this? 1 over 2. Right? 1 over 2. Now, why is that? Well, it's like if I add 2 to x, I actually move in the negative. So you actually, this 2, it's not what happens to the graph, it's what you have to do before you do anything to the graph. So because the 2x is doubling, alright, where I look, when I bring it back, it's now, that value is half the distance from where it was. Right? So the value at 1 was at 2, so it's now half. Right? Makes sense? Sort of more difficult to look at, but so all of this is about trying to help you remember what each one of these things does. Right? So, where does that lead us? Well, let's go back to one thing we talked about. Completed square form of a quadratic. Completed square form. Do you remember that?
Yes.
So, let's have a look at a completed square form Alright. So if I say to you, f of x equals x squared, alright, if I then said to you, express this quadratic in function notation, so f of x, whatever, okay, so you're using an f, you're using brackets, you're using, right, x in there, right, how would you write this in that form, bearing in mind f of x is x squared, and also, what would the transformation be? So there's going to be multiple transformation, but looking at that, first, what would function notation be for it? And what would the transformations be? What combination of transformations would have happened? Everyone okay with what I've asked there? So it's going to be a combination of translation, stretch, so on, reflection maybe, I don't know. That's what you're going to be saying. Alright? Give it a few minutes, think it, write it on your book, and then we'll chat about it.
Minus plus minus 2.
Okay, so we said the thing that won't be in there is a squared. So what we have to do is take out the things. If that's the initial function, right, x squared, so you write is x plus 2, f of x plus 2, right? Then we've got the minus 2,
And then 3 that goes in.
and then we've got the 3. Okay. Then the next question is, what is the transformation? What's the combination of transformations?
Shifting to the right.
Well, let's use proper vocabulary. So translation. Well, no, we don't say left and right. How do you describe a translation?
By that vector.
Vector, yeah? So what would the translation vector be? What would it be? Minus 2.
Minus 2 minus 2.
Minus 2 minus 2. So I've got that and that. Well, the first thing we looked at is what do you do when you add or subtract something onto the function. Remember, it shifts it up and down. A translation has an x component and a y component. What we did was break those up into two different parts. Right? So there is a translation of -2, -2. Also what? Stretch.
Vertical stretch.
Okay. Vertical stretch. Factor 3. Okay. So that's what we're thinking is going to happen. So let's just have a look at what that will actually look like. So here is x squared. If I put in the one that I've just put in, so y equals 3. Sorry. 3 times x, what did I say, plus 2 and squared, and then minus 2. Right, we reckon, well, what do you expect is going to happen? If you're looking at a graph, what do you think, based on what we've just said, it will sort of move to the left, it will move down, and it will squash in, you think? Is that what you're expecting? Yeah? Now the thing is, the reason why this was very useful, can you see now that the completed square form of a quadratic is useful because if a quadratic vertex is always at 0, 0 when it's just x squared, the plus 2 bit and the minus 2 in the function, so the x plus 2, well, which point is the easiest to translate? The vertex. Start at 0, 0, and if I translate from 0, 0, the translation vector will give you the coordinates that it ends up at. So it will end up at minus 2, minus 2. So that's why the completed square form was really useful. So if I can put it in completed square form, I know the coordinates of the vertex. That's why we went through it before. Right? So that should maybe open your eyes now why the completed square form works the way it does. Right? Make sense? Any questions there? No? Okay, so what you're going to do now, right? So starting page 24, alright, you have a series of questions to do. Alright, so pages 24, 25, 26, 27, all transformations. I would like you to do a range of, they're all exam style questions of different levels of difficulty. So pick a range of them that you're going to challenge yourself at. Alright, we didn't do anything with reflection here. So make sure that when you pick some, you do some with reflection, things like that in there. Make sure you pick a range where it's not just draw the graph, but also write the function. You'll notice that there is a review exercise which is non-calculator and a review exercise that is with calculator. So try and do a bit of both. Right? So that's page 24, 25, 26, 27. I'll let you work on from there.